right, in 10.2, we are going to take a look at something called the fundamental principle of counting, or fundamental counting principle. Anytime in mathematics that somebody puts the word fundamental in there, it means it's really important. There's a fundamental theorem of algebra. There's a fundamental theorem of calculus. There's a couple others as well that you encounter, and this one is for counting, okay? So to start with, we're going to take a look at factorials. I don't know if you have seen factorials before. Some of you probably have. Some of you probably haven't. Factorials are notated by an exclamation point. So for any counting numbers, right, 1, 2, 3, 4, and so on, n factorial means I take n and I multiply by 1 less than n and 1 less than that, all the way down to 1. So I have n times n minus 1 times n minus 2, all the way down to 3, 2, 1. Definitionally, I mean, that's the definition of factorial notation anyway for counting numbers. But 0 factorial is the value 1. And you might kind of feel like it's what happens when we talk about exponents, right? We saw exponents happen back in chapter 4 when we were looking at, place values, 2 to the 0 powers 1 kind of stuff. Anything to the 0 powers 1. It kind of has that feel to it. It's a definition because it doesn't fit with the other category, right? I can't go 0 down to 1 because 0 is already below 1. Like, it doesn't make sense with the first definition. It's its own definition. And we're going to need it to fall into place like that for some other things we're going to do. So there's a reason it's defined that way. But it's not like something somebody can prove to you at all. It's just a definition. You just have to take it at face value, right? Like, what does the color red look like? Well, you have a picture in your mind as soon as I said it. Somebody defined it for you that way, right? Same idea. Okay, so we're going to take a look at an example. Number 1 has 5 factorial. So with our definition that we had back, the first definition on the previous slide, this means I'm going to multiply 5 times what? 4, and then 3, and then 2, and then 1. That's all it means. Now, if the numbers are small enough, that's not so hard to do, and you probably don't even need a calculator for some of them. But if you want to grab your calculator because they're going to get big pretty quick, feel free to do so. What is 5 times 4 times 3 times 2 times 1? It is 120. Okay, the next one, well, the top's a little bit bigger. It's 8 factorial. And I could write it out, 8 down to 1. And that's what I'm going to do first. I'm going to show you a shortcut in just a second. But for the moment with me, just write down 8, 7, 6, 5, 4, 3, 2, 1. That's the numerator. And then the denominator is 4 factorial. What will it look like? 4, 3, 2, 1. What I want you to notice is that everything after the 4 matches exactly, right? And the other thing I want you to notice is that it's all multiplication. Everything is multiplication. So somewhere in middle school, you learned that when you do multiplication, you have the ability to reduce things, right? If you've got all multiplication on top, all multiplication on bottom, and there's a factor that divides everything, you can do that and you can reduce a fraction, right? It's a middle school thing. So when we're thinking about that, we can utilize that here as well. So the 4, 3, 2, 1s can cancel. And that allows us to simply multiply 8 times 7 times 6 times 5 for my answer. So what is 8 times 7 times 6 times 5?
15.
What is it? 1600?
1680.
1680. Thank you. Okay, so what we did there was perfectly fine, but there is a shortcut to it. So I want to show you that because it will become more valuable the bigger our numbers get. So instead of writing 8 all the way down to 1, I'm simply going to write 8 out until I get to 4. And at the point when I get to 4, I can't just write 4, it's 4 factorial because it's representing everything that comes after it that I'm not writing down. And then on the bottom, I have the same 4 factorial that I was given to begin with. When the factorial pieces match exactly, which they do now, right? 4 factorial on top, 4 factorial on bottom, I'm allowed to cancel those out. I can't reduce, so it's not like if I have the 8 factorial at the beginning and the 4 factorial at the beginning and say, hey, look, I can just divide 8 by 4 and I get 2 factorial. No, I don't. You can't do that. You can only do it if they match exactly, because what we're actually doing is we're dividing out 4, 3, 2, and 1, all of them, right? So when I do that, I'm left with that same 8765 that we were when we wrote them all out longhand. And on this problem, it doesn't really matter. I mean, it didn't take us that long to write those pieces out. But can you imagine if it said 52 factorial on top and 48 factorial on bottom? Do you want to write 52 down to 1? Me neither. Nor do I want to write 48 down to 1. So if there's a place that I can stop and get them to match perfectly with the factorial notation, then I've eliminated part of the work I have to do. Does that make sense? Okay. So we're going to take a look at some larger valued ones. In fact, the next one is that already. I have a 20. It's not 52 yet. We will get to 52, but we have a 20. So we're going to write the first one out until we get down to what? The top one? 10. And what we're looking for is we're looking for it to be matching something on bottom. So whatever the largest piece on bottom is, which these two have 2 identical pieces, so that's not a great descriptor. But if they had been different, we would stop at whichever one was larger. So I have 20, 19, 18, 17, 16, 15, 14, 13, 12, we're almost there, 11, and 10 factorial. And on bottom, one of those 10 factorials, and it doesn't matter which one, so I'm just going to make it the second one so they kind of are close to one another. I'm going to leave as 10 factorial. The other one, however, I have to write out. So the second one, or the first one, the way I've written it, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay, I'm going to do the hard part. There you go. 10 factorials are gone. That's not the hard part, right? Okay, here's the deal. At this point, could you multiply everything in the top out and multiply everything in the bottom out and let your calculator do the division? You could. And on this one, it would probably work. However, sometimes the number's still too large on top to do that. And if you try, your calculator will either error out if the number gets too big, or more likely, it will turn the number into a scientific notation form. And you're going to be like, I don't know what this means. It says 3.473265 E7. And I'll be like, oh, E7. When it puts that capital E in your calculator, it means it's turned it into scientific notation, and you no longer have the exact expression. That's not very helpful for what we're doing, okay? So I want to show you that everything on the bottom, will cancel out with things on the top. So one of the ways that we can deal with this, instead of just letting the calculator do all the division, is look for things that will reduce. Some of them reduce really nicely. For example, take a look if I look at, say, 10 times 2. What is 10 times 2? 20. I can almost group the 10 and the 2 together and cancel at the same time with the 20. I kind of like grouping 2 pieces or 3 pieces together when I see them. I can't do that all the time, but sometimes it's nice. Do you see any others that group? I don't see any others actually that group now that I did that one. Oh, I do. I see another one. Do you see another one?
4 times 3.
4 times 3. What is 4 times 3? 12. So that one reduces. And it's also probably worth mentioning that if you reduce them in a different way, you're still going to get the same answer. So it doesn't matter what reducing you see. As long as it's correctly reduced, you'll still end up with the correct result. That might be it. In pairs. Is that it in pairs? I think it is too. So then we're going to just go piece by piece. Tell me something on top that divides by 9. 18. If I divide 9 by 18, I'm left with a 2 on top. How about the 8? 8 will work with 16. So 16 divided by 8 gives me another 2. How about the 7? 7 will divide the 14, giving me a 2. They don't always give 2s, I promise. It's just working out that way this time, okay? How about the 6? What was that?
We got rid of the 12 already.
We did get rid of the 12 already. It will still reduce with the top. If you don't want to deal with it, you could just leave it till the end and use it as a division factor. That's fine. But you could also take a look at pieces that are able to be reduced, which I'll let me come back to that in just a minute. Let's do the 5 and you'll see what I mean. What about the 5? 5 and 15. So the 15 will actually become a 3. What is 6 if you break it down to its factors? 2 times 3. Do you see some 2s and 3s? Yeah. So you could actually do the pairing on top if you wish now to cancel with the 6 on bottom. Does that make sense? You're just looking for pieces to cancel. Okay, here's the trickiest part of doing what we just did. It's writing things neatly enough and carefully enough that you can go back and not miss anything that didn't get canceled out. So you do need to be careful on your writing. I'm not looking at your writing, but it's going to catch you on your writing, and there's no way for me to know that that's what happened in terms of partial credit. So you have to use some caution and some carefulness. Maybe you want to get a highlighter. That's fine. Maybe you just want to circle things in a different color. I would strongly encourage you to do something to make sure you don't lose any of the factors. So there's a 19 here. I'm going to circle them actually. I'll box mine. Ooh, I don't want to do that. Let's try that. I have a 19 and a 2, 17 and 2, 13 and 11. Those are the pieces I have. And I warned you already, you're going to use your calculator. This is definitely the point where the calculator is necessary, right? So grab your calculator. We're going to multiply 19 times 2 times 17 times 2 times 13 times 11. Say again. 184,756. That's what I have written down too. Does everybody get that? Okay, all good? Okay, we're going to take this a step further and abstract it a little bit. Here we're actually given a formula. The formula has some n's and some r's in it, and some factorials. And it actually tells me what the n's and the r's are over here, right? So I'm just going to take the step that happened sort of before number 3 was given to us and put those numbers in place. So the n is the 28. So I have 28 factorial on top. The r is the 15, so I have 15 factorial on bottom. And then n minus r, which is 28 minus 15, another factorial on bottom. This formula is coming from somewhere. Next class, you'll see where it's coming from. But for right now, it's just given to you in the problem. All right, so starting with, what's 28 minus 15? 13. That's 13. So I'm just going to rewrite this with the 13 there instead. So I have 15 factorial over 13 factorial. So unlike the last one, the two pieces in the denominator don't match. So technically, you could write the 28 down to 15 or the 28 down to 13. It wouldn't matter. But I always stop at the one that I can stop at first. So I would write 28 down to 15 if it's me. So we're going to write down 28, 27, 26, 25, 24, 23. I need more space, so I'm going to shift some stuff. $22, $21, $20, $19. Oh my goodness, still not enough. That'll be 18, 17, 16. There's my 15 factorial finally showing up. And I have the 15 factorial on bottom. And then I need to write the 13 down. So 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so there's a little bit of tediousness in some of these because they do go longer, but not all of them do that. Some of them will stop much shorter than that. Okay, so first we can cancel out our 15 factorials, right? All right, so can you tell me any pairings that will cancel out? I'm going to go with whatever pairings you guys pick because there's lots of options. Which one? 13 and 27. 13 And 26. How about can I do 13, 2, and 26?
Yeah.
Are you good with that? Like that. Oops, not there. Here. All right. 13, this 2, and the 26. Something else. 7 which? 3. Okay, so the 7 and the 3. 7 and 3 make 21. So those cancel. 5 and 4 make 20. So that cancels. Eventually we're going to run out of pairings, and that's okay too. We may be there. Are we done? I think so. Let's go down our list then. How about my 12? 12 goes into 24. 2 times. What about my 11? 11 goes into 22. 2 times. My 10, unfortunately, I already canceled out the 20, so let's just skip it for the moment. We'll come back. How about the 9?
18.
Yep, the 9 will go into the 18. 2 times. How about my 6? Which one? 6 won't go into 16.
I think we're getting 8 because we're getting
They go to 28.
No. Okay, so we're stuck with the 6 for the moment. Okay, so a couple things we could do. Did I skip over an 8?
Yeah.
I skipped over my 8. I'm so sorry. How about my 8?
6.
The 8 will go into the 16. Yeah. Okay. Let's actually break the 10 and the 6 down. That's something else we could do. So how will 10 break down in factored form? 5 and 2. And the 6 will break down as 3 and 2. Okay. So if you notice there's, let's see here, I got lots of 2s that I can cancel out upstairs, right? A 2 here and a 2, there's lots of 2s. So let's just pair up a couple of those. So we'll take this 2 with this 2 at the end. And I'll take this 2 here with the 5, 2, and the 2 toward the end as well. How about the 5 and the 3 then? Can I cancel those?
You could put the 5 into 25.
You could. The 5 into the 25 would work. So we'll do the 5 into the 25 to give me a 5 here. And how about the 3? 27 it is, yeah. 27 divides by 3 to give me what? 9. Okay. So let's use that same green. I have a 28 and a 9, a 5 and a 2, 23 and 2, 19, 17. I think I'm done. So if you grab a calculator, what does that give you? You're not even going to tell me the number in right? 37 million.
37,000.
It's okay. 442,000. 37,442,160. Yeah, that's a lot of digits. And can you see how it would be so easy to miss one of these numbers in the midst of everything you canceled? So be very, very careful with your cancellations, okay? Okay, we haven't actually gotten to the title of the section. What was the title of our section? Yeah. I didn't write the 1, but it doesn't matter because when we multiply or divide by a 1, it doesn't change the value. Yeah, you're right. You can do it in any of the numbers you can use. It does not have to be in a specific order. Yes. Okay, so the title of our section was Fundamental Principle of Counting, and we're finally ready to actually say what that is. The fundamental principle of counting talks about doing some kind of a task that has multiple components. So if you have a task that consists of k separate parts, where the number of ways to do the ith part is n sub I, then the number of ways to perform the task is n1 times n2 times n3 all the way down to nk. And it sounds so much harder than what it is. Just write it down and be okay. Promise. Okay, so you did a task like this morning. You got dressed. All right, so what are the different components that you had to make a decision about? Well, at the very least, your shirt and your pants, because you're all wearing them. I can see that, right? You're all wearing something on the top and on the bottom. But you're all wearing shoes too. And so there's different components, and you can't like wear 2 shirts and no pants. That's strongly discouraged. So you can't like intermix these things together. They are separate choices that are made. These are the K tasks that it's talking about. So if you went to your closet and, ignoring whether things matched or not, you simply counted the number of shirts and you counted the number of pairs of pants, and we'll just use those 2 categories for right now, you could come up with a total number of different options you had for getting dressed this morning with just those 2 components. But you could make it more complicated, right? We could add in our shoes, we could add in undergarments, we could add in hair accessories or earrings, you could add in jewelry, things like that. All that kind of stuff could be added in, and the process becomes much more complicated. And that's what you're seeing when these are written out, is that these are different components of some kind of a task. Okay, multiple tasks within a larger task. Now what we're going to apply this to first is something we did back in section 1, which is our committees of people. Do you remember our group of students? Okay, so I totally lied to you. We're going to actually come back to them again in another lesson too, but we're going to talk about them right here. Instead of trying to create the list to figure out how many different ways we could create these groupings, we're going to do this now with the fundamental principle of counting. So, we have a president and we have a treasurer, correct? We have 2 choices to make. That's what we did when we made our list as well. So for the purposes of us making our choices, I'm just going to make sort of like placeholders, okay? Before we listed people's letters in them, like we listed an A and an N, or we listed a B and an M, or something like that, right? What we're going to list inside of these now is the number of options that we have. Okay, so how many different people can be president with this description? 6. 6, right? It doesn't say only boys or only girls. Any of the 6 people can be president, correct? Now, once you pick the president, however, you do not have 5 choices left for your treasurer. Why not? There's 5 people. It's supposed to be the opposite sex, right? And so since it's supposed to be the opposite sex, we need to be careful. Whatever happened on the first choice, we've eliminated everybody else that's that same person's sex from being chosen in the second spot. How many choices do we have in spot number 2?
3.
Just 3. Right? Does that make sense? So, what is 6 times 3? 18. Please flip back and take a look at 10.1, problem number 1. How many did we get? We had 18. Which one was easier to do? This one was, right? Fundamental principle of counting is wonderful if all I care about is how many options I have, right? I don't have to list them out to do that, although that was the way we could have done it. All right. Number 6. It's the same thing, same people. President, secretary, treasurer, but now we have additional constraints. So I have 3 positions that I'm trying to fill. 3 positions My president, my treasurer, my outside pieces are supposed to be the girls. So how many girls do I have to pick from in my category of names? 3. So there are 3 options in the first place. How many options are in the last place?
2.
There are 2. Once I've picked those 2 people in those 2 places, how many people are left to pick for my secretary that's in the middle? 4. Why is it 4 and not 3? Yeah, it's all the boys, which are 3, plus whoever didn't get picked from among the girls, right? There's still 4 kids, or 2 people, whatever, that could be in this third spot, which is the center spot. And we multiply, because the fundamental principle of counting says we multiply these individual pieces together. And what is 3 times 4 times 2? 24. Does it match what we did in 10.1 problem 2? I think it does. 7's harder. Because it has this, there's like a catch. All right, we have a committee. The committee's 2 people, so it feels a lot like the first problem. I list out 2 options. How many people could I select from for the first sort of position in my committee? 6. And how many for the second position? 5. So what is 6 times 5? 30. What was the answer I got on number 3 from 10.1? So why?
Repeats.
What repeats?
You can't repeat within. You can't like just switch them around because it's just a committee. It's not 2 different positions. So you have to
Right.
divide by 2.
Yes, you're right. So what happened when I did this is I said that I could have both, say for instance, AB and BA. They would both be included in the 30 that I just listed, right? Because I put some ordering in this that's not really supposed to be here in the problem as it's really designed. What I did is I double counted all my groups of people. So this 6 times 5, man, I'm writing too big. Let's try that again. The 6 times 5 double counts. And it double counts everything, right? Everything got double counted, which means exactly like Elena said, everything then needs to be divided by 2 to remove the double counting. So we get this number, 6 times 5, and we'll divide by 2. And we're doing this to remove the double counts. It isn't that this problem's hard, it's that it's tricky, right? There's a catch. Yes?
So if it was like 3, would we just divide by 3? If there's like 6 times 5 times 4?
Yeah, well, it's a little different. We won't have ones quite like that. There's going to be another strategy we use when we have more combinations of things, but I wanted to put this one in here because I wanted you to see the connection back to the earlier section. Yeah, you won't see much of this going on with anything bigger. You won't see anything of it going on with anything bigger. This should be 15 to remove our double counts. Okay, you ready to look at some other examples? We're going to look at some tests. That's what we're going to look at. Quizzes. They're short. All right. Determine the number of possible ways to mark an answer sheet with an answer for each question, for each test. So not answering it is not an option. That's what they just told you. There's not 3 options, true, false, and nothing. There's 2 options, true, false. Okay? All right. So the first test is a 6-question true or false test. So it's a 6-question test, which means I'm going to have 6 little lines. You want to think of this kind of like I'm randomly guessing. Randomly guessing. How many different things could I randomly guess? Different ways could I randomly give my answers on this test? Well, it's a true-false test. So how many different answer choices, if I answer all of them, do I have? 2. So each one of these blanks has a 2 in it. And with the fundamental principle of counting, I'm going to multiply all those together at the end. So what is 2 times 2 times 2 times 2 times 2 times 2? Is it 64? There are 64 ways that I could mark my true-false test. So the idea that randomly guessing is going to result in a perfect score is pretty minimal, right? Only one way of randomly guessing out of 64 is a perfect score. So it's not likely to happen. But it becomes even less likely if I don't have true false and I have the example number 9, which is a multiple choice test. So I still have my 6 choices, or 6 questions. But now instead of 2 choices for each of the answer choices, how many choices do I have? 5, right? It says there's 5. So I have 5 in each of my place value spots, or places anyway. And what is all those 5s multiplied together? 15,625 ways. So if you're randomly guessing, are you more likely to do well on the multiple choice test? Truly random guessing, right? Not educated guessing. That's something completely different, right? Truly random guessing. Are you more likely to do well on the true-false test or on the multiple choice test? True-false, because there's fewer ways that you could mess it all up, right? Yeah. So with a true-false or a multiple choice test, we would have that many. Okay, we're going to do a 5-question test now, or quiz. This one says test. Well, whatever. 5 questions. And it tells you that there are 5 answer choices where each one is used exactly once. So if you want to write down the pictures you have in your mind is something like matching or test bank. You know, you've got a test bank. So once an answer's picked, it's eliminated from the test bank. I know sometimes professors give tests that don't do that, but your history tells you that's how it should be, right? It should be like that. There's a test bank. I use each answer once. Imagine it's like that. So there's 5 answer choices, and I can only use each answer one time. So the first answer or first question that I pick, how many choices do I have for my question's answer? There's 5. But once I use that one, now how many choices do I have? 4. And then I would have 3, 2, and 1. We've already done this today.
So it's just 5 factorial.
It is 5 factorial. And what is 5 factorial? 120. There's 120 ways, if I'm doing a matching style test or a test bank style test, that I could answer those 5 questions. So it's not quite as nice as the multiple or the true-false one, right? This is also 5 choices instead of 6, but it's definitely far less than if I had multiple choice. Because if I had multiple choice, these would all be 5s, right? That'd be much bigger value, even with a 5-question test, than if I would have a matching kind of test. But sometimes there's answer banks where they give you too many things in the answer bank, right? You've all been there with her, right? You don't use them all, but you use some of them. And you've got this one. So we've still got our 5 answer choices. Our 5 questions. But instead of 5 answer choices, I have 10. So I start out with a 10 here, and then I would have 9, 8, 7, and 6. So it's not a factorial, but it's actually something we saw earlier too. Not with the numbers here, but this is really 10 factorial divided by 5 factorial. That's what it is. Because the 5 down, like 5 down to 1 is no longer there. We've sort of divided out by it. You don't have to know this. I just want you to see that it is something of a factorial notation. So what is 10 times 9 times 8 times 7 times 6? 30,240 ways. Yeah, multiple choice tests, true, false, fill in the blank. Lots and lots of ways to mess it all up, right? That's what that will leave. Yes. If you're just guessing.